These students were approached by somebody. Is she here? This lady about a project. And they came to me and said, this is what we'd like to do. Surely you jest. Surely this isn't a senior design project. And they got talking about it. The more they talked about it, the more intriguing it became. The more complicated I realized it was. So this is a first for us. We have not done this kind of project ever. They're going to spend the next hour explaining to us how this is a legitimate project, and you'll find out pretty quick. Alex is the boss. Let her start.
All right, thanks, Dr. Euler. So thank you guys for coming out today. If any of you had the privilege of watching any of the previous presentations, I hope that you enjoyed them. It's been very exciting to watch all of my classmates work on their projects throughout the semester, and I know they're all really proud of what they've put forward. So as Dr. Euler said, we're removing the Franklin Glass Dam. I'm Alexis Wiesenberg, the project manager, and on my right is our environmental team.
I'm Laura Drebecki.
Nicole Me.
I'm Erica Reiser.
And on my left is our water resources team.
I'm Adrian Garcia.
And I'm Pat Asenius.
And together at the beginning of the semester, we combined to form Free Flow Environmental. We decided that the dam removal would be a really great project because it perfectly combined the specialties that we're all focusing on. Additionally, we personally connected with this project because we're all interested in revitalizing the environment, in particular stream restoration. So this is just a brief overview of where our project is located. It's in Butler County, in the city of Renfrew. You can see on the northern shore of the dam. The dam is outlined in red, and on the northern shore is the dam owner's property, and on the southern shore is the Saxonburg Area Authority water plant. The dam crosses over Connoquenessing Creek, and just upstream of the dam it branches into Upper Connoquenessing and Thorn Creek. So as Dr. Euler said, we reached out to American Rivers, and they basically agreed to take us on as consultants for this project. The reason that Franklin Glass Dam in particular is being considered for removal is because it's very outdated. It's no longer being used for its original purpose, which our environmental team will go into more detail for. And it's also impeding fish migration and natural river ecosystems in the area. Additionally, this watershed that we were working in is the most undammed watershed in Pennsylvania. They've already completed 11 dam deconstructions, and this dam deconstruction in particular would reconnect 5 miles of stream habitat. So that in itself is another reason why it was very important for this to go forward. You can see the deliverables that we'll be giving to American River at the conclusion of this project. The design and restoration waiver package is a combination of everything that we did, and that's compiled of our environmental team's impact assessment, the hydraulics and hydrology analysis, and our construction management package. It's important to note that Pennsylvania has a pretty streamlined process for getting approval for dam deconstruction processes. They recognize that these projects are very low risk to the environment, and then in the years following the deconstruction, it provides huge benefits to the ecosystems in the area. So they've worked together with American Rivers to create a more efficient process. Because of that, and because of the fact that other states don't recognize this, we really wanted to go into much more depth than the state actually requires. So a lot of the analyses that we're going to talk to you about today are things that you may see other states requiring, but Pennsylvania has recognized that these projects are so valuable that they don't necessarily require them. So you may be wondering, why are we taking out dams? Dams, we mostly learn about all of the benefits that they have. They control floods, they can provide irrigation, a small percentage of them provide hydroelectric power, and a number of them are used for recreation. So if I just told you all of these great reasons to put in a dam, why would we want to remove them? Or what is the dam problem? There it is. Third, 4 times the charm. Get it up there. So in Pennsylvania, there have been 72 recorded dam-related drownings. So safety is a huge issue, especially in a dam like ours where the water is flowing over the top. It creates a high turbulence region which traps people and causes them to drown. Additionally, economically, when a dam reaches that state of disrepair, the dam removal costs 3 to 5 times less than repairing it and maintaining it, so removing it is the more economically sustainable option. And Wisconsin Department of Natural Resources in particular defines their dams as one of the largest threats to their aquatic biodiversity. So all those things combined, like once a dam's no longer serving its original purpose, there's really no reason not to remove it. So this is a picture of the Franklin Glass Dam in particular. You can see this picture here is looking at the dam with a little bit of a view upstream. It's a low-head dam with a spillway cut out on the north side. So during normal flow conditions such as this, water is flowing out of the spillway. And then during a normal storm event, water actually goes over the top of the dam and then acts as a weir. So it's not providing any flood control to the upstream area. And then on the right, you have a picture looking downstream. So we examined a couple of different alternatives. A majority of the plan went forward with alternative 1, and our environmental team will go into detail about why we chose that. This alternative is basically removing the dam and allowing the sediment to flow downstream in a controlled manner. The only reason you wouldn't be able to do this is if the soil is contaminated or if there's an excessive amount of sediment, so allowing it to flow downstream would suffocate the downstream environment. And alternative 2 is if one of those scenarios were true, then we would remove the dam but dredge the stream for the sediment. Alternative 3 is doing nothing, and our environmental team talks about why that's a greater risk to the environment. So now I'll pass it off to Laura to go into our environmental impact assessment.
Thanks, Alex. I'm going to talk about the environmental team's deliverable for this project. Just like Alex said, this is considered by the Pennsylvania government to be low risk to the environment, so we wanted to prove that our site follows what their opinion is. So to do that, we did a phase 1 and phase 2 environmental impact assessment, and we did it with the standard, the ASTM standard. Phase 1 is more qualitative, while phase 2 is more quantitative. For phase 1, we did a historical site research. We did record review and interviews with the current owner, and we also did a habitat assessment. And then for phase 2, we actually went on site, took samples, took it back to the lab, and we did water quality analysis, sediment analysis. We also analyzed all of the alternatives. We did a Leopold risk matrix to see, for each alternative, to see which would be the least risk to the environment, and then we decided which was the best alternative. And we also created a future monitoring plan. I'd also like to note that we spent about 25 hours on site taking samples and about 10 hours in the lab getting our results. So I'm going to go into more detail about the historical site research. Until 1868, the site was used as a sawmill, and it wasn't until 1907 that the Butler Short Line came in, and that is railroad tracks that run parallel to Connoquenessing Creek. That ran from 1907 to 1931. Also in 1907, there was a coal-fired electricity plant built on site that was used for the Butler Short Line until the 1920s. And then it was converted into a glass manufacturing company. That's actually when the dam was built on site in the 1920s, so that we don't know the exact year. So it was used until the 1940s for glass manufacturing, and also it is used for glass manufacturing because you need about 1 ton of water to cool the glass for production. And it went through different companies, and it went to finally the Franklin Glass Company, so that's why it's the Franklin Glass Dam. In the 1940s it closed down, so since then the dam has not been used for its original purpose. We couldn't find any information between the 40s until about 10 years ago, but we know that it wasn't used for its original purpose. Currently the site is privately owned. That building is used as a workshop and office space, and once again the dam is not in use. On October 4th we took a site visit and we met with some government officials, and they gave us all of the government records for the dam. And we noticed that the DEP inspection from 2004 showed that the dam was showing lots of spalling, cracking, and deterioration, and also potential holes underneath the water line. The water line. So they said that the dam needs to be fixed and maintained, or it should be removed. And then in 2009, when they went back for another inspection, they noticed the same things, only it was becoming even more of a problem, which makes sense since concrete does deteriorate at an exponential rate. So that's when it became an official candidate for removal. When we had our interview with the landowner, he said that he wants it to be removed because of the liability and safety issue, because people use this creek as a place to use their kayaks, and they get out onto his property and walk around the dam, which is a really bad safety issue. It's steep. The dam is about 6 feet tall, and there's lots of rocks, so if someone would fall and get hurt, that would be bad, and it would be a liability issue for him. So during phase 1, we did a rapid bioassessment upstream and downstream. This is out of 200 points. There are 10 categories that we looked at. Each one ranged between 1 and 20 points, totaling up to 200. So it just gives a snapshot of the health of the site. Upstream, we noticed that there was heavy sediment deposition. You can see an example here. There was about 2 feet of this above the dam, and it has a foul odor. And you can see it's very small particles. There are man-made, and that is bad because it suffocates the habitat, so it makes it harder for fish to survive. We also noticed that the water was very slow-moving and glassy, which is also bad for fish. And then there is a bridge abutment with a bridge, and then also a dam, which it doesn't give much of a habitat for the animals. So this got a score of 62 out of 200, which is marginal. We went downstream and we noticed improvements. The sediment was much better. It had all different sizes, which is healthy for the animals. The water was flowing at different rates. Just by looking at it, we could tell, which is good. The banks were well vegetated, and we actually found a live mussel, which you can see in the picture there. So this got a score of 158 out of 200, which is suboptimal, much better than marginal. So we know that the dam is not the only reason why upstream would have a lower score, but we think that it does have something to do with it. So we're hoping that by removing the dam, the score upstream would become closer to the score downstream. So now I'm going to pass it to Nicole, and she's going to talk about phase 2 testing and results.
So we did a water colony analysis to see if some of the known negative effects seen in larger dams could be seen on our Lowhead Dam. Some of the things we were looking for were in the impounded area behind the dam. We were looking for increased temperatures and pH levels, lower dissolved oxygen levels in the stream due to the increased temperatures in the water, increased algal growth due to standing water, and also a higher concentration of suspended solids in the water. So we looked at 8 different sampling locations. We have 4 locations just behind the dam in the impounded area, 1 location just downstream of the dam, and then zooming out a little, we have 2 locations about a mile upstream of the dam on each creek that contributes to the area behind the dam, and then 1 location about a mile downstream on Connoquenessing Creek. And so we found upstream, in the sampling locations upstream of the dam, we had DO concentrations of about 88 to 90%. In the locations downstream of the dam, we did notice slightly elevated dissolved oxygen levels, but overall, all readings we took in the site were over 80%, which is considered good in a stream. And we also found for total suspended solids, total dissolved solids, and pH levels were all within the range of normal for the stream. We also looked at the sediment impounded behind the dam. We did a sediment probe test to determine the amount of movable stream bed material that could wash downstream when we removed the dam. So we did multiple probe tests in multiple locations, and this cross-section is the cross-section looking downstream closest to the dam, so just before the dam where you see the most buildup of sediment. And as we mentioned before, the dam does have a large spillway on this cross-section on the left side, so most of the buildup was on the right side, so most of the buildup was on the left side of the bank. And we estimated this volume to be about 4,500 cubic feet, which compared to the size of the stream and the fact that the downstream habitat has been starved of sediment for so long, this volume was not a concern moving downstream. However, it would be a concern if the sediment was contaminated. So based on previous site history that Laura talked about, the DEP does require for this site that we test the sediment behind the dam for contamination. We did not get our results from that test back within the scope of this class. We actually expect them next week. But we went ahead and did an analysis of, based on site history, what potential contaminants could be in the stream, and then if we, in the sediment behind the dam, and then if we did find those, how they might move downstream. And some of the things we looked at were a low weight PCB, a high weight PCB, and benzoate pyrene. And these are both things that potentially could have an impact on animals or humans. So we made a transport model. This treats the sediment behind the dam as a source, and we looked at sediment water exchange of chemical loss to the atmosphere, sedimentation of solids in the water, also degradation, and also flushing from our spillway. We're all taken into account. So based on a hypothetical concentration that we find in the sediment, we looked at how that would impact the water and then how that would move downstream once the dam is removed. So potential impacts on water, based on the lowest effects level scenario, we found, so if we found the lowest concentration that could be a concern in the sediment, which again, we don't have our results back yet, so we don't really expect this. But if we did find the lowest effects level in the sediment, we determined that benzoate pyrene and the high weight PCB did not even have a concentration in water that could be a potential issue. We did find that if we found a low weight PCB or something like PCB 33, we would be concerned about contamination in the water. We would probably require either additional water quality testing, or they would tell us to remove the sediment. But again, we do not know our contamination results yet. And now Erica will talk a little about the risks of the project.
Thanks, Nicole. So in order to compute and compare the environmental risks of each alternative, we used a Leopold environmental risk matrix. So the purpose of this matrix is to provide a qualitative review of the site, and it determines the magnitude of environmental impact as well as the magnitude of importance of these impacts. So the matrix is split up into actions and factors. So the actions which will cause the impact are modification of regime, which is things such as modification of habitat, noise, flow modification, things like that. Land transformation and construction, which can include dredging, cut and fill. Land alteration, which is like landscaping and erosion control measures. Resource renewal, which can include fertilization and waste recycling. And then accidents such as operational failures or spills and leaks. And then the factors, which are the things that can be affected, are split up here into physical, biological, and cultural. And you can see underneath some of the breakdown of these factors. So I included a section of one of the environmental risk matrices. So this is actually for alternative 1. And you can see in the pink, I highlighted just an example for you to look at. So this box right here, so the left box in each column is represents the magnitude of impact, and then this column represents the magnitude of importance. So in the case of endangered species, obviously if there are endangered species on the site, the importance is very high. We'd have to keep up with restrictions for that, and it'd be very risky to do a construction project on a site with endangered species. So that's why it's a 10 for importance. And then we actually don't have any endangered species on our site, so the impact is a 1, which is the lowest it can be. So that's just an example so you can understand how the matrix is used. So like I said, the scale is 1 to 10. 10 is the largest or most important, and 1 is the smallest. Here is kind of a summary of each alternative's risks. So you can see I highlighted the smallest in green and the largest risks in red. And you can see that alternative 1 has most green, which means it's the lowest impact, the lowest risk. Alternative 2 is also very low risk, but slightly more than alternative 1. And then alternative 3 is the highest risk by far, and that's if we left the dam in. So just to summarize the findings, opinions, and conclusions of our phase 1 and 2 environmental impact assessment, we concluded that the upstream and downstream water quality results are all in acceptable ranges for this stream. The volume of sediment flow during deconstruction is acceptable. So if we needed to, we could let it flow downstream and it wouldn't cause any harmful effects to the environment. The sediment sample contamination results have not yet been received by Free Flow Environmental, but based on similar dams in the area, it's likely that the sediment is not contaminated, and we will be using this as an assumption to move forward with the project from here on out. The habitat assessment showed that the dam is impacting the upstream environment, and then the Leopold matrix computations determined that alternative 1 has the lowest risk, and this is why we'll be choosing alternative 1 to move forward with the hydrology and construction plan. So a little bit about future monitoring for this site. We are required to monitor the site for 60 days after deconstruction, so that's based on our seeding, so we need to ensure that vegetation grows back in that time. A follow-up site visit is scheduled for 1 year after the dam is removed, and this is to check for excessive erosion or scour holes or anything else that could be caused by the dam removal and the stream changing shape. And then you can also conduct a habitat assessment to confirm ecosystem stabilization. So we would compare this to the downstream and upstream habitat assessment that we have already completed. And hopefully the upstream environment will get a greater score. And then you can also confirm new results to our baseline data for water quality, fish species, and population, things like that, just to show that the dam removal did have a positive impact. And now I will pass it off to the hydraulics and hydrology team.
Thank you, Erica. So the purpose of the hydraulics and hydrology report was to sort of determine what are the current conditions in our watershed and our floodplain, and how are those going to be impacted by the dam removal project. So in order to complete this, what we did was we did initial data gathering, including precipitation data, spatial data, and then we actually went out to field to do cross sections. So we did surveying, and then using that, we were able to create a basin model to estimate the discharge hydrographs, and then use that input into a hydraulic model that we use to evaluate the changes in the water surface elevation. So the precipitation data was downloaded from the National Oceanic Atmospheric Administration. So we used a rain gauge that was located inside the watershed, and we downloaded an intensity duration frequency curve. So what this gives us is based off of a storm of a certain magnitude, so perhaps a 1-year storm, which you would expect to happen once every 1 year, or a 100-year storm that you would expect only to happen once every 100 years, we're able to get the intensity of the rain for a certain duration. And using those values, we're actually able to create our design storms. So starting from the middle, going outwards with our, we're able to use the durations for the 1-hour durations, the 2-hour durations, the 6-hour durations, 12-hour durations, and 24-hour durations to create the shape for our design storm corresponding to those return periods. Afterwards, we downloaded digital elevation model data from the USGS, the United States Geological Survey, and we used that to delineate the watershed using the Franklin Glass Dam as the outlet point. So the dam is located just downstream of the Connoquenessing Creek and Thorn Creek Junction, so this watershed incorporates both of those. Standard protocol was followed, including finding the flow direction, flow accumulation, and eventually determining the stream network. To determine some of the hydrologic properties of the watershed, the National Land Coverage Database was used and reclassified into 4 main types of land use. And then the soil types were downloaded from the Web Soil Survey run by the United States Department of Agriculture. And using the properties of land use and the soil type, we're actually able to determine the curve number and create a grid corresponding to that. And using these parameters, we're able to create sort of more qualitative analysis of the watershed. So the watershed was further delineated into subcatchment zones based off of the confluences of the stream network, and we're able to use a tool called HEC-GeoHMS, which is a toolbar in ArcGIS that allows you to prepare your data in ArcGIS and import it into HEC-HMS for your basin model. So we're able to calculate a couple more geometric properties and prepare our model to estimate discharge. So here's the HEC HMS model, and what we do is we take this is our watershed, it has our properties based off of the vegetation, or the soil types and the land use, and we apply the precipitation that we had calculated earlier from the design storms to it, and from that it computes the discharge at the outlet point, which is what we want. So to determine sort of the normal flow conditions, we applied an average daily rainfall rate, which we took from the average annual rainfall rate divided over a number of days in the year, and we applied that precipitation model to the basin model until the discharge was reached a steady state. And so these are the values we used, about 80 cubic feet per second. If we apply the 1-year storm to the basin model, we're able to get a peak discharge of about 3,000 cubic feet per second. And if we're looking at a 50-year return period design storm, we're looking at 14,000 cubic feet per second. So we're able to use these different discharges in our hydraulic analysis to determine what is the floodplain and how is that going to change if it does change. So now I'm going to pass it off to Pat, who will talk to you a little bit more about the field survey we performed for this project.
Thanks, Adrian. So in order for us to utilize our ArcGIS and HEC HMS data, we needed to gather accurate bathymetry data and geometric data from the site area. So we went out to the site 3 separate times, and in order to measure the cross-section accurately, we took a 200-foot string and marked it at 5-foot intervals. From there, we were able to have some of my colleagues here go through the stream with the surveying pole and take 5-foot increment measurements. So total, we took about 300 points of cross-section data. Here you can see the cross-section data inputted into ArcGIS with a heat map of elevations. Just something to point out is right near the confluence of the 2 streams, we have a very big scour hole, which makes sense because you have 2 streams forming one. So just to sum it up, we went to survey 3 separate days for a total of 16 hours, and if you include man hours for the fact that we had typically 3 or 4 people surveying, it came out to 58 man hours. So from this data, we created a 3D topography map in AutoCAD Civil 3D, and we took from that cross sections 14 and cross sections 13. 14 is right near the dam. We were not able to survey this due to risks. Given with the fact that people do die going over the dams, we didn't want to take any chances near the spillway. So you can see right here is an example of a quick grade profile from Civil 3D with the stations labeled at 5-foot increments to keep it consistent with our survey data. So I'm going to pass it back to Adrian to talk about the site-specific HEC-RAS model.
Thanks, Pat. So we use HEC-RAS, which is a program developed by the U.S. Army Corps to sort of analyze river systems. So using the topographic map, we're able to sort of delineate the geometry of the project site. So I used the HEC GeoRAS toolbar in ArcGIS to delineate to signify the river center lines, the bank lines, and the cross-section cut lines. So using that, we apply the discharge that we had calculated from the HEC HMS model, and we're able to calculate what is the water surface profile along Connoquenessing Creek with existing conditions as is, and in the new conditions without the dam. So in the top image, you can see the water surface profiles with the dam in place, and you can see the bottom of the dam, or the thalweg, the lowest point in the river. So what we see in the bottom picture is the new condition with no dam in place. So what we notice is that there's not really a huge change in the larger storm events. We only really see that change in elevation at normal flow conditions. And this makes sense because this is a low head dam. We've seen actually the water flowing over the top of it like a weir. So it's not surprising to us that the water is already overtopping the dam, even at a magnitude of a 1-year flood. So what this means is that if we remove this dam, it's not going to significantly impact the floodplain downstream where there are some residences, so they can't say that our removal of the dam is what caused their place to flood. So we're able to kind of show that you only really get changes in the lower water surface elevations. So now I'm going to pass it back to Pat, who will actually, not yet. So sorry about that. So we have a couple kind of demonstrations of what's going on here. So we have the model in HEC-RAS with the Connoquenessing Creek converging with Thorn Creek and going downstream into the dam. And once again, we have the surface elevation. This is just for the baseline flow, so the one that is mostly impacted by the presence or the removal of the dam. The middle line you can see is the confluence with Thorn Creek. And you can see right there where it dips down in the Thalweg is the scour hole that forms from the junction. Here is the new condition where we have the water surface elevation that dropped by about 4 feet in the impoundment area. And so that's sort of the normal conditions that we'll expect to see. So now I'm going to pass it back to Pat, and he'll talk to you about the more expansive model he created to really study the floodplain and the surrounding area.
All right, thank you, Adrian. So as Adrian said, we did the site-specific model just to get the difference from the dam being removed at baseline flow. So we wanted to create a more expansive floodplain analysis, given that the existing FEMA maps are dated at 1989. So what we did was we took GIS data that was previously used and imported it into HEC-RAS. Also imported our surveying data. So we have here extra cross sections that were cut from the DEM data at distances of the following. You can see in the chart here, 0.83 upstream of Connoquenessing, 0.87 miles downstream, and then 1.15 miles upstream on Thorn. So although the dam will not affect the floodplain to a high degree, we still wanted to import the dam and the ineffective flow areas to keep our surveying data and geometry correct with the elevations. So we calculated ineffective flow areas both for this model and for the site-specific model using a 4-to-1 ratio going upstream and a 1-to-1 ratio going downstream. So you can see here in the bottom right table all of the cross sections that are affected by the dam being in place. Additionally, you can see in the bottom left a heat map of velocities. So we see a higher velocity right at the spillway and lower velocities on the southern shore, which makes sense because the spillway is on the north shore. Additionally, you see higher velocities downstream after the spillway, which is signaling a change in the water surface profile. So from there, we did an encroachment analysis in order to get a detailed floodway and floodplain map for FEMA. So an encroachment is just simply the elevation that a developer will need to build to in order to not change the base flood by more than 1 foot. So in order to optimize for this, we used HEC-RAS encroachment tool. HEC-RAS has 5 separate methods for encroachment. The one we chose was method 4, where you give it a targeted water surface change for each profile. And you can see in the red boxes here, the most downstream cross-section changed 0.91 feet above the base flood elevation, and the cross-section directly upstream of that is 0.96, which is right in the range of what we wanted, which was a maximum of 1 foot. Additionally, we also optimized for top width. We wanted a smooth transition between cross-sections that also was consistent with the DEM elevation data. It is important to note that due to the topography of the region, which was displayed on the DEM data, upstream of the confluence of Connoquenessing and Thorn Creek is a very steep ravine, so the floodway does match the floodplain pretty closely in many instances. With that, we exported our data from HEC-RAS into Civil 3D, and this is a map overlaid on top of Bing Maps through Civil 3D. The green lines represent the floodway water surface profile at each cross-section, and the teal lines represent the floodplain water surface elevation at each cross-section. So this is our final FEMA map product. We have in the gray here zones AE. We have the board up here if anyone would like to look at it afterwards. I realize it's a little blurry. So zone AE means that the base flood elevations have been determined. Previously on record, the FEMA maps were only determined for Connoquenessing, so all of Thorn Creek was in zone A where they had not determined the base flood elevations. This is a close-up of the town of Renfrew, which is about 3/4 of a mile downstream of the dam. It's important to note that this area was already in the existing FEMA floodplain, so we did not flood their town by removing the dam. And just here's a list of addresses that are affected by the floodplain. For example, on 102 East Main Street, which is right about at the intersection of Main Street and Meridian Road, they would expect to pay, if they're 1 foot beneath the base flood elevation, $3,800 in insurance premiums per year for $125,000 of coverage. That only includes the basement and the contents within the basement. I got that data from NFIP, or the National Flood Insurance Program. So with all that analysis, I'm going to pass it to Alex to talk about the deconstruction plan.
Thanks. So as Erica stated earlier, the deconstruction plan went forward with alternative 1, which is saying that the dam is being removed and we're allowing the sediment to flow downstream. This is a picture of our site access plan. We'll be accessing the site from the southern shore, and there are a couple of reasons for that. You can see based on the topographic map that the southern shore has a much milder slope than the northern shore, so just as far as bringing the excavator down there, it's going to be a lot easier. Additionally, there's much less vegetation because the Saxonburg Water Area Authority has a cleaner bank line. We did get permission from them to access the site from this side, as a side note. Additionally, the private bridge on the owner's part only has a 10-ton weight limit, and they had concerns about protecting the deck of the bridge, so they didn't want us crossing that with construction equipment. This here is a picture of the northern shore, just put at the dam needing the abutment. There's some unknown or unidentified culvert pipes that lead into a storage tank. None of these are in use, and the DEP was unable to provide us with drawings for these structures. So we're leaving them in place with the permission from the DEP and the dam owner, just to not alter the slope stability, decrease the project costs, and since we don't have any plans for them, we don't want to risk breaking them down. Additionally, you can see we have our erosion and sediment control devices on here. So there's a rock filter downstream of the dam, 2 fish barriers upstream of the dam, and I have the stockpiles located on here as well. So rumble pads will be placed at Renfrew Road, where the equipment will be going on and off county roads. The purpose of this is to prevent our site soil from tracking onto the roads. This is a pretty standard construction practice. An alternative, if the water authority were to request it, would be a full site access road, which would be a higher cost. It would take longer to install, and typically isn't used for a project of this size. Additionally, as I said, we'll be installing a rock filter downstream, so this is a standard construction detail. The bulk of it will be R4 riprap because the stream depth can reach greater than 3 feet, and behind that is AASHTO number 57 rock, so that's just a smaller grading of rock to allow it to trap some of the smaller sediment. The purpose of this isn't to stop sediment from going downstream, but to control the release. If the sediment's not contaminated, the downstream environment will be starved of sediment, so we want to slowly allow it to re-infiltrate the downstream environment. The fish barriers are just netting that you string across the upstream area, and the purpose of that is also to prevent fish passage into the site. After these are installed, we would stun the river. It doesn't hurt the fish. That's just to make it easier for us to transport them to the opposite side of the rock barrier so that we don't harm them during the deconstruction process. Finally, we would install silt fencing anytime that we need to keep a stockpile on site. And that's just a standard standard construction detail for the silt fencing that we would be using. So now I just want to go through the basic deconstruction sequencing. This is a picture looking at the southern shore of the dam. So the excavator with a hydraulic hammer would track in and begin positioned on the northern shore. It would use the hydraulic hammer to take out a 1 foot deep by 3 foot wide section, depending on how high the water level is. The reason for this is to control how much water is flowing. We want the water level to be equalized before we begin the entire deconstruction to prevent a risk of the dam breaching, and also to prevent high flows through the area. So the excavator will take out those 1 foot deep sections until the water level is equalized. Once that happens, he'll begin deconstructing the dam from the southern side to the north. The excavator that we have has a reach of approximately 25 feet. And since the river is 75 feet wide, we will have to track into the river. The downstream sediment, or the downstream stream bank, should be strong enough to hold the construction material, but as an additional precaution, as he's taking down the dam, some of the dam rubble is going to be placed to create sort of a platform for him to walk out onto. And then this here is the beginning of the abutment that we'll be leaving in place. All of the concrete is planned to remain on site as long as we remove any of the reinforcement that's found within the dam. The reason for this is because if we grade it down to sites or sizes similar to that seen on site, it will aid in making a more well-graded soil within the stream bank. That combined with the sediment that will be flowing downstream will aid in allowing animals to rehabitat the area. So I created a design schedule and a construction management schedule. This is just a snapshot of the design schedule. It's scheduled to be 375 days or approximately 75 work weeks. American Rivers had already completed the data gathering portion of this when they handed the project over to us, so we've been responsible for the preliminary design. You can see the duration is approximately 140 days or 25 work weeks, so we cut down on that time and completed that work for American Rivers. We'll be handing over our design documents to them, and they will be getting a design firm to review our documents, and that will be the final design portion that you see on the schedule. And after that, those documents will go out to bid, and that's the final portion of the design. Following that is the construction schedule. The overall project duration is approximately 68 days, but that's due to the post-project monitoring that the construction manager will be responsible for. They'll actually only be on site with construction equipment for approximately 7 days. So the construction management plan consists of mobilization, deconstruction, restoration, and demobilization. The only requirement for the timing of this was to make sure that our seeding started August 1st or later. So you can see with the asterisk next to August 1st, that just means that I made our project schedule for seeding start on that date. That worked out well because it made the rest of the project start around the end of July, which helped us to avoid fishing season. There's no legal restrictions on fish in the area, so we really just wanted to make sure that we avoided high flow periods and things like that. Here's the estimate that I put together. The total project cost is about $62,000, with the design being $20,000 of that. So by completing the preliminary design, we saved American Rivers approximately $10,000 of that cost. The deconstruction will cost about $42,000, and you can see the further breakdown of the deconstruction costs on the right. So for this plan, I did still want to address the other alternatives, even though the environmental team did a great job of analyzing all of them. I just wanted to put cost and actual risk number to them. So I used this risk assessment code matrix, which judges probability and severity on a scale from 1 to 5, and then those numbers are multiplied together to give each event a risk assessment code. The codes range from low, which is numbers between 1 and 4, up to extremely high, which is 20 to 25. Our highest risk activity was inclement weather, which had a number of an RAC of 16. This is due to the fact that we can't complete the deconstruction during high flow periods. So since the project deconstruction is only 7 days, if we have a storm event, that could significantly impact the time that we are needed to be on site. A full dam breach was also given a high RAC of 15. This is because although it would accelerate the project, it would cause extreme harm to the downstream environment. That rapid release of water and sediment could cause scouring and erosion, as well as suffocate the downstream environment, so we don't want that to happen. Additionally, I examined the cost of if the sediment results come back and say that the soil is contaminated. This has an RAC of 8. It would cost the project approximately $12,000 and would delay the project approximately 3 weeks. If the soil comes back and is found to be hazardous, that's an entirely different story. It would nearly double our project cost based on how far we have to transport the material. There's only one area in Pennsylvania that is qualified to accept it. So if the sediment's hazardous, basically the project would just be shut down. If there's excessive sediment or excessive concrete on site, we'd like to maintain it on site as much as we can, and that's why the RACs are extremely low. There are very few circumstances where we would need to track that off-site, but I did a cost analysis just in case. So in summary, the deliverables that we'll be handing over to American Rivers include the Phase 1 and environmental impact assessment, a hydraulics and hydrology analysis, and a construction management plan. They'll be using that information to get approval for the deconstruction from the DEP, and hopefully the deconstruction will be able to be completed in July of 2017. So with that, we'd like to thank, first and foremost, Lisa with American Rivers. She was a huge help to us this semester, and we're so glad that she trusted us to be her consultants for this project. Additionally, we worked with Ben Larson from the PA Fish and Boat Commission, Jack Kruder from the DEP, and multiple professors from Pitt, including Dr. John Euler, Dr. Carla Ng, Professor John Sebastian, and Dr. David Malhorn. So with that, I'd like to open it up for any questions.
So the problem with that was that we weren't able to find a gauge that was kind of in the zone. That was an issue. I think the nearest gauge was something like 6 miles downstream from the project site. So we kind of ruled that out because of the proximity wasn't kind of close enough.
The one thing we did get though, when we spoke to the dam owner, I asked him what the highest he ever saw the water level at was, and it was qualitative, but he told me it was at his front step of his building, which kind of follows what we got in our HECRAS model, but that was during Hurricane Irene or Hurricane Ida back in the early 90s or late 90s.
Well, there is high water there, because I got it. Because I went through that site, so I would be personally curious to see how your design matched to past flood. How large was the watershed?
It was about 136 square miles.
Square miles. And what portion of that is the full?
I'm going to estimate about 1/3 of it was Storm Creek, the smaller one, and then the other section was for Pine Nest.
And on your design storm, what was the storm duration used for that?
So we used a 24-hour.
24 hours, does that seem reasonable to you? 24 hours, I'm just asking.
I think since it's close to Pittsburgh, and we definitely had rain events for 24-hour periods, we decided to use that.
All right, on your HECRAS, I noticed there's a couple bridges on your overhead, but I didn't see any cross sections of the bridges. You're talking about 100-year flow from there, or those bridges that get impacted by the flood?
They're already in the floodplain, so we assume that the design that they had already took that into account. We did, however, use ineffective flow areas in the model to model it correctly. Well, we could have taken that into further account.
For the environmental, are there any wetlands in that area?
We went out with DEP and they decided there are no wetlands on either bank. The banks are both kind of steep going into the stream, so we didn't put a wetland seed mix. I think we used the riparian.
How large
bank.
of a lake surface area that dam created?
I'm sorry, I didn't hear.
Surface area of the
How big
impoundment.
was the lake surface that dam created?
Oh, the impoundment?
It definitely went past both of the upstream bridges, was pretty much flat and glassy.
Yeah, we tried walking
That's
down.
about 400, 500 feet upstream on each creek from
Yeah,
the dam.
we tried walking to see if there was a riffle that we could,
we were
that we
trying
could
to-
find, and we walked forever, and we couldn't find any.
Yeah, we tried to locate upstream where like the impoundment stopped. We were looking for the first riffle of where you can see like rocks in the stream bed, but we couldn't find it through walking up the stream, and it's a very dense area.
Yeah, on your last question on your disposal area. I heard that it was hazardous. You had only one site to go through, otherwise you're going to ship it downstream. What if it was somewhere in between, wasn't hazardous, but for some reason you didn't want to send it downstream? Did you identify perhaps a local disposal area you could put it?
Yeah. If it's hazardous, I will not let it flow downstream. I will personally
You're saying
return.
if it's not hazardous, but it's
Yeah, if it's just contaminated but not hazardous.
Right.
It'll go to the Seneca landfill, which is about 15 minutes away from our site, and I actually contacted them to get the quote for disposing of the material there. That's where I came up with the additional $12,000 as well as the project delay. Not all of that is the cost of disposing it there. Some of it is the additional man hours and the additional rental fees that we'd have to pay for our equipment. But yeah, I contacted them, Seneca Valley Landfill, or Seneca Landfill.
Good job.
Any other question? Yep.
Is it a trout stream?
Yes,
It is trots.
there are trout.
Good place to fish.
It'll be even a better place to fish now. You're welcome, fishing community. Any other questions? Yes.
So, do you have any ideas what would happen long-term with, soil and vegetation cover in this region? So is there any selling point there, or, you're just saying we want to remove the risk, maybe improve the ecosystem, but what would happen when you remove the dam? What would happen with, attractiveness of that region altogether?
Right, so part of our agreement with the Saxonburg Water Authority for accessing the project from that site is we'll be doing a little bit of a revamping of their bank system there. So immediately on site, we'll have the riparian seed mix, so there'll be a lot of natural plants growing back in the area, and we'll be doing a little bit of landscaping on the southern shore. But the purpose of coming back to the site a year afterward is to make sure that the stream is reforming in a good natural way. We don't really like to control how the stream reforms itself by trying to regrade or plant too much. It's best just to let it reform naturally. But yeah, there would definitely be a walkthrough a year later, and if necessary, we would add more vegetation and things like that. Does that answer your question?
Yeah.
Okay.
Good job.